Welcome to MarkScheme. Work, energy, and power. Everything you need, made visual. Here's a roller coaster car. Engine switched off, just coasting. Simple question. Without measuring a single force, can you tell me where on the track it's moving fastest? Watch it run. You already know the answer in your gut. Fastest at the bottom of the dips, slowest at the top of the peaks. And you can prove it without ever touching Newton's laws, just by following the energy. Up high, the car stores energy in its height. As it drops, that stored energy turns into motion. Energy transferred, never lost. That single idea, work, energy, and power, is one of the most powerful shortcuts in all of physics. Here's exactly what we cover, straight from the syllabus. Physics, topic 8.3. Work and the two ways to find it. Force times distance, and the area under a force-distance graph. The three kinds of energy you need: kinetic, gravitational, and elastic. The principle of conservation of energy that links them. Energy transfers, drawn as Sankey diagrams. And finally, power and efficiency. And the good news, exactly as with kinematics and forces, every part of this is standard and higher level common core. There is no higher level only content in a point 3 at all. All of it is on both the SL and the HL papers. So this one video serves both. We'll lean on force and velocity from the earlier videos, but nothing new is assumed. Let's define the currency of this whole topic. Work. When a force pushes an object through a distance, it transfers energy to it. And we call that energy transfer the work done. The formula is force times distance times the cosine of the angle between them. Work is measured in joules. 1 joule is 1 Newton pushing through 1 meter. Why the cosine? Because only the part of the force pointing along the motion actually does work. Drag this box with a force at an angle theta, and it's the horizontal component, F cosine theta, that drives it forward. The cosine simply picks out that useful part. The stunning consequence: if you push exactly perpendicular to the motion at 90 degrees, cosine 90 is 0, so you do no work at all. Carrying a heavy bag along a flat floor, the lift is vertical, the motion horizontal. Transfers 0 work to the bag. There's a second, powerful way to find work, and it should feel familiar from the graph's video. Plot the force against the distance moved. The work done is simply the area underneath that graph. For a steady force, it's a rectangle. Force times distance, exactly matching the formula. But the graph method is more general. If the force varies, like a spring that gets harder to stretch, you just take the area of whatever shape appears. Same rule every time. Work is the area under force versus distance. Energy comes in many forms, but 3 appear again and again in mechanics. First, kinetic energy, the energy of motion, 1/2 mv squared. Notice the velocity is squared, so doubling the speed quadruples the kinetic energy. That's why stopping distances explode at high speed. Second, gravitational potential energy, the energy of height. Lift a mass m by height delta h, and you store mg delta 8 joules in it. Let it fall, and you get that energy back. Third, elastic potential energy, the energy stored in a stretch or squash. Pull a spring of stiffness, k, a distance x, and you store 1/2 kx squared. Every one of these three is in your data booklet. You don't memorize them, you locate them. Now the crown jewel of the topic, and it's the roller coaster from the start, made quantitative. On the left is the car's energy, split into two. Kinetic energy in green, gravitational potential energy in blue, stacked into one column. The car starts at rest at the top of the track, so all of its energy is potential. The column is pure blue. Now let it go. As the car drops into a dip, the blue potential energy pours into green kinetic energy. It speeds up. Climbing the next peak, the green drains back into blue. It slows. But keep your eye on the total, the very top of the column. It never moves. Every joule of height that disappears reappears as a joule of motion, and the sum stays locked at 200 joules. That is the principle of conservation of energy. In an isolated system, energy is never created or destroyed, only transferred from one form to another. Two forklifts lift identical crates to the same shelf. They do exactly the same work. So what's the difference between a cheap one and an expensive one? Speed. Power is the rate of doing work. The energy transferred divided by the time it takes, measured in watts. 1 watt is 1 joule every second. And there's a beautifully useful second form. Power is work over time. Work is force times distance. So power is force times distance over time. But distance over time is just velocity. So power equals force times velocity. When something moves at a steady speed, V against a resisting force, F, the power delivered is simply F times V. That one line, P equals FV, cracks open a huge class of exam questions. No real machine turns all the energy you feed into something useful. Some always leaks away, usually as heat and sound. Efficiency measures how good the machine is. The useful output divided by the total input. Because output can never exceed input. Conservation of energy again. Efficiency is always a number between 0 and 1, or as a percentage, never more than 100%. The clearest way to picture it is a Sankey diagram. The width of each band is proportional to the amount of energy. All the energy flows in from the left as one wide band. Then it splits. The useful part carries straight on, and the wasted part branches away. And crucially, the total width is conserved, in equals out. The wider the useful branch compared with the input, the more efficient the machine. A narrow useful branch and a fat wasted branch is a machine dumping most of its energy as heat. Let's build a ladder of examples, easy to hard, all my own numbers. Number 1, straight from the definition. A rope drags a crate 4 meters along the floor, pulling with 50 newtons at 30 degrees above the horizontal. Find the work done on the crate. The force is at an angle to the motion, so we need the cosine. Work equals 50 times 4.0 times cosine 30. Cosine 30 is about 0.866, so that's 200 times 0.866, about 173 joules. If you'd forgotten the cosine and just multiplied 50 by 4, you'd have said 200 joules and thrown marks away. Number 2 shows off the real power of energy. A 2-kilogram ball is dropped from rest and falls 5 meters. Find the speed just before it lands. You could reach for suvat, but watch how energy conservation does it in one line. As it falls, gravitational potential energy is converted into kinetic energy. So the PE lost equals the KE gained. mgΔh equals 1/2 mv squared. Now the magic? The mass appears on both sides and cancels completely. Rearranging, v squared is 2gΔh. That's 2 times 9.8 times 5, which is 98, and the square root is about 9.9 meters per second. Suvat would give the exact same 9.9. But the energy method jumped straight from height to speed, with no acceleration, no time, no signs to trip over. When a question only involves heights and speeds, and asks for one of them, energy is almost always the faster road. Number 3. Puts P equals FV to work. A motor hauls a 200 kilogram load straight up at a steady 0.5 meter per second. Find the power the motor delivers. The word steady is the key that unlocks it. Because the load rises at constant velocity, it's in equilibrium. So the lifting force exactly balances the weight, mg. Now use power equals force times velocity. That's mg times v, which is 200 times 9.8 times 0.5. 200 times 9.8 is 1960. Halved is 980. The motor delivers 980 watts, near enough 1 kilowatt. Number 4. The hardest ties efficiency to the Sankey picture. A machine takes in 500 joules and delivers 350 joules of useful output. Find its efficiency. Straight from the definition, useful over total, 350 over 500. That's not 0.70 or 70%. And the missing energy hasn't vanished. Conservation of energy forbids it. 500 in minus 350. Useful leaves 150 joules wasted, almost always as heat. Draw it as a Sankey. 500 joules flow in, the 350 useful branch carries on, and the 150 wasted branch peels away. The widths add back to the input every time. Now the exam craft that separates the top grades. 1. The biggest time saver in this whole topic. When a problem involves only heights and speeds, use the energy method. Potential energy equals kinetic energy instead of Suvat. No time, no sign conventions, often a single line. 2. Never drop the cosine theta in the work formula. And remember, a force at right angles to the motion does no work at all. 3. Efficiency is always less than 1, less than 100%. If you ever calculate more, you flipped useful and total, so recheck. 4. For steady speed lifting or dragging, use power equals Fv, where F is the force being opposed, the weight when lifting, friction when dragging. And 5. Every equation here lives in your data booklet, so don't waste effort memorizing. Find it, quote it, substitute, and finish with units and about 3 significant figures. That habit banks the method marks. Finally, the 4 traps that quietly cost marks. 1. Forgetting the cosine theta in the work formula. Only the component of force along the motion does work, so an angled force always needs it. 2. Mixing up the energy types. Kinetic uses velocity squared. Gravitational potential uses the change in height. And elastic uses the extension squared. Grab the wrong one, and everything unravels. 3. An efficiency over 100%. That's physically impossible. So if you get it, you've divided total by useful, instead of the other way around. And 4. The sign of work. A force that opposes the motion, like friction, does negative work. taking energy away. But remember that energy is only transferred, never truly destroyed. It becomes heat. Dodge these foreign work. Energy and power become some of the most reliable marks on the paper. And that's a point 3. Work, energy, and power. Fully covered. Work as energy transferred, kinetic, gravitational, and elastic energy. The principle of conservation of energy, tying them together. Power as energy per second. And efficiency, with its Sankey diagram. Every part of it is on both the standard and higher level papers. Next in the course, we change gear completely and follow a disturbance traveling through space. The wave model. For more, that's markscheme.app. See you there.